The turn of the 20th century, landline telephones, incandescent lights. This is the Western world around the time the first semiconductor device was patented. Unrivaled progress in electrical engineering followed, a new technological revolution confined to institutional settings by the high cost of making semiconductors. More than 70 years would pass before Russell Dupuis, Daniel Dapkus, and a disruptive new manufacturing method would open the floodgates, unleashing the most advanced electronic technologies across the globe, changing it, and us, for good. One grew up on acres of wheat, the other in the Chicago hustle.
We didn't have a lot of advanced electronic projects on the farm. Of course, the space race was going on.
And I thought for a while that, boy, it'd be wonderful to be an astronaut. As time progressed, I realized that they were sending pilots up there, and I wasn't a pilot.
When Dupuis and Dapkus met in the lab of Franklin Institute medalist Nick Holonyak at the University of Illinois at Urbana-Champaign, they owed their friendship to a technological revolution from outer space: semiconductors.
Things like silicon and gallium came out of star explosions and ended up here, stuck in this dirt somewhere.
And in Holonyak's lab, the two saw how the different types of semiconducting stardust could be combined to make groundbreaking new lasers and LEDs, technology with the potential to launch a new era of global communications. And yet, the building blocks could only be assembled under lab conditions. Mass production was impossible. As the years passed, Dupuis found potential in an idea from late chemist Hal Manisevic, a machine that would blast the ingredients into something of a high-tech snow globe and build devices layer by layer as the snowflakes settled.
I started building my first reactor in July of 1975.
Dupuis was working at Rockwell Labs, where Dapkus would join him in developing MOCVD.
Most of the people I talked to said, "You're wasting your time. That technique will never work."
But the reactor worked perfectly, liberating years of innovation that had been confined to the lab.
We made electrically operated lasers, and it turns out that these lasers were better than what anybody else had made before.
Suddenly, the millions of lasers needed to build the world's communications networks could be mass-produced. Millions of miles of fiber optic cables gave life to the internet.
So now we can Google Lady Gaga and see what she's up to on any particular day of the week.
And you can do it from your smartphone because the parts that connect mobile devices to cell towers are made with MOCVD. The process is shrinking the power accessories for your devices, making energy grids more efficient, and powering spacecraft with advanced solar cells.
All of the cells that SpaceX is putting up are cells made this way. So his 20,000 near-Earth satellites for telecom are going to be all based on this technology for power.
The snow globe technique unleashed affordable LED technology. Because of LEDs alone, forecasts predict a 40% cut in U.S. energy usage by 2030. As MOCVD evolves, a new world emerges: brighter, greener, smarter, and more connected than ever.